Hey everyone, so let's see, we're in the middle of the proof of the fundamental theorem of Galois theory, and so we want to complete that. We're going to complete it today, and so we're going to prove parts B and C. And if you remember part B, it gives us this connection between normal subgroups of the Galois group and normal extensions. Okay, so let's get going there. Now, so let me, okay, now remember, it's an if and only if statement, right? G is a normal subgroup of the Galois group if and only if this particular, right, it's this extension here, phi of G over phi gamma of K, right? So let me write it down. So G is a normal subgroup of gamma of L over K if and only if this extension right here is normal. All right, so that's what we want to prove. Oh, and I should point out one thing. So I wrote this a little bit differently, right? So in the last time, this is phi of gamma of LK, right? And I wrote it out in full notation, but this is the quicker, easier way to write that, and these are exactly the same thing, right? So here's what we want to prove is this one right here. And before we get going, so let's say before we prove the assertion, we need a preliminary fact. And we're going to use this in part B, and if I remember correctly, we also use this in part C of the proof. And so let's just see what's happening here. So let's let M be in script F, right? So it's an intermediate field that's living in between L and that guy right there. Yeah, so in fact, let's say it like this. So phi gamma of K is contained in M, which is contained in L. And in fact, and I want this little inclusion right here, I want to call that inclusion star. I'm going to use that in a second. So if sigma is in gamma of LK, which is equal to little gamma of K, by the way, then if we look at sigma of gamma phi K, this is equal to gamma phi K. So why is that? And so the reason, because gamma phi K is fixed by every element of gamma K right? I mean, that's by definition, right? So, sorry, I spaced out for a second. So, by definition, right, every element of this is the subfield fixed by every element of gamma K, by definition. So say and, what else? oh yeah, and sigma of L is equal to L. So now what I want to do is I'm going to apply sigma to star. So applying sigma to star, we get, so let's see, I'm going to have sigma of phi gamma k contained in sigma of m, contained in sigma of L, and then let's replace what we have here. So I know that sigma of this piece is equal to that piece, so that gives us, so we can say, so phi gamma k contained in sigma of m contained in L. And so what does that tell us? It tells us that sigma of m also lives inside script f hat. So it follows that, where'd it go? Sigma of m is an element of f hat. Okay, fine. So what does that mean? Well, if you live in f hat, then you can apply gamma to it, right? Any element, the domain of gamma, little gamma, is script f hat. And so, so this means we can apply little gamma to sigma of m. Okay, so, and that's what we want to do. So, so we will show that if I apply gamma to sigma of m, that is equal to sigma, let me get this right, sigma, yeah, gamma of m, sigma gamma of m, sigma inverse. And I want to label this equation right here. I'm going to call that one double star, and we're going to need this double star. This is the preliminary fact that we need. It's that double star. So so here we go. Right, I want to show equality of these two sets right here, and so go like this. So tau is an element of the left-hand side if and only if, okay, so what does that mean? So this is the group of automorphisms of L that fix everybody in sigma of m. Right, so that would mean, and in fact, let's write this out. So this is gamma L over sigma of m. Right, and that's true if and only if tau of sigma of little m equals sigma of little m for all little m in capital M. Now what I want to do is I want to hit both sides of this equation by sigma inverse. So this would be if and only if sigma inverse tau sigma of little m equals little m for all little m in capital M. And so what does that say then? That says that sigma inverse tau sigma fixes every element of capital M. So that would mean, so if and only if, sigma inverse tau sigma is an element of, so who would that be? It would be, well, gamma of Lm, which is little gamma of m. Okay, so then what does that tell us? Well, if you hit both sides now with, well, hit on the left by sigma and on the right by sigma inverse, then we have, so therefore, tau is in gamma of sigma of m if and only if tau is in sigma gamma of m sigma inverse. Right? And so that proves the equality of those two sets. So let me write it down one more time. So thus, gamma sigma of m is equal to sigma gamma of m sigma inverse. Okay, so that's the equation that we're going to need to make use of. Okay, now, so what do we want to do? We want to prove we're going to start with the assumption that we have a normal subgroup, and then show that we've got that the corresponding extension is normal. Okay, so that's the forward direction. So, right. So now, suppose that G is a normal subgroup of gamma L over K, which is little gamma of K. Okay, so now what's our goal? Let me just remind you. So our goal is to show that the extension fixed field of G over fixed field of gamma of K is normal. Okay, so since phi gamma of K contained in phi of G contained in L and L over gamma phi of K is Galois. That's according to theorem 5.4c. Since it's Galois, that means normal, so that's the part we care about, so hence normal. To show that the one we're interested in is normal, so to show that phi of G over phi gamma of K is normal, we can apply, so what I want to do is apply theorem 3.5, which means that we would show so this means show that if sigma is in gamma of L over phi gamma of K, which is equal to, I need to sort of spread this out here a little bit. In fact, let me put it over here. So show that if sigma is in gamma of L over phi gamma of K, which is equal to gamma, where'd it go, gamma of phi gamma K, which is equal to gamma of K, which is equal to, this is gamma L over K. And the equality right here, these are equal because of what theorem? This was from 5.1, right? So we get equality right here from 5.1. So show that if we choose sigma in here, then like something's weird here. Oh no, that's right. Yep, no, that's right. So then sigma of phi of g is equal to 5g, right? So if we can show that, remember this equivalence between normality and leaving certain fields invariant, right? That's the content. That was that three-part equivalence that we had. That was theorem 3.5. Okay, so let's pick sigma in gamma of LK. Then G, let's put it over here. So G, that's equal to sigma G sigma inverse. Why is that? Because it's normal. So because G is normal in gamma LK. This is equal to sigma of gamma phi G sigma inverse. This is because gamma and phi are inverses. And now I apply double star, so this is equal to gamma sigma of phi of G. So that's by double star. Okay, so I have this equation now, and what I'm going to do, I'm going to apply phi to both sides. So applying phi to both sides. So front side, back side, what we have is phi of G is equal to phi gamma sigma phi of G. Now, where am I here? Right, and this cancels out, so this is equal to sigma of phi of G. Now, this holds for every sigma, and so by theorem 3.5, the extension is normal. So this would be phi G over phi gamma of K is normal. Okay, so there's the forward direction. Now I need to prove the reverse direction. So now I'm going to assume that extension is normal, and I need to show that the subgroup's normal. This one's a little bit quicker. So on the other hand, if our extension phi G over phi gamma K is normal, then by theorem 3.5, every time we take a sigma, so let's say every sigma in gamma L over K satisfies this same equation that we had a second ago. So sigma phi of G equals phi of G. And so now G is equal to gamma phi of G because of the inverse relation. So gamma phi of G, which is equal to gamma sigma oh, right, yeah, I'm substituting. Okay, that so yeah, phi of G is equal to sigma phi of G. So this is going to be sigma phi of G. Now I'm going to apply double star. So this will be sigma gamma phi of G sigma inverse, which is equal to, we've got inverses here, so this is sigma G sigma inverse. All right, so now that tells us that the subgroup is normal. So therefore, G is a normal subgroup of gamma L over K. Okay, so that completes the proof of part B. And notice, there's really, in a sense, this proof right here is taking all the stuff that we proved, various theorems, and putting them all in one place, right? So, in a sense, we've almost proved, we've essentially proved this theorem, and now we're putting all the pieces together and just saying it all in one place. Okay, so now for part C, so now what we want to do is assume that we have a normal subgroup, and then we're going to say something about a particular quotient, right? So let's see, I want to assume that G is a normal subgroup of gamma LK. So now, that should be a B. Sorry, I have a typo in my notes here. Let me just fix that. So by our previous part, then we know, so by part B, we know that phi of G over phi gamma of K is normal. Now, okay, so now I'm going to use that theorem 3.5 again. So by theorem 3.5, if sigma is in gamma of LK, then then sigma of gamma of G, phi of G is equal to phi of G. So what? Well, so what that means is that every time we take a sigma, right, in the Galois group, we can restrict it and view it as an automorphism from phi of G to phi of G. So thus, each sigma in gamma L over K restricts to an automorphism from phi of G. Let's see, do I need to use any notation? No, let's just say phi G phi of G, and this automorphism, so let's say that fixes gamma phi of K. Sorry, I said that backwards. Phi gamma K. So, and I want to describe this in an alternate way. So let's say let's start with put another way. The mapping from gamma L over K to gamma of phi of G over phi gamma K given by, it's just given by restriction, right? So given by sigma goes to sigma restricted to phi of G, this is a homomorphism. So the restriction map gives us a homomorphism. Is a homomorphism. Right, and what I want to do, I want to apply the first isomorphism theorem to finish the job. So the kernel is the sets. Okay, so what would it look like? It would be it's the set of all automorphisms. So this is the set of automorphisms of L. Now, what would they have to do to fix the kernel? I mean, or to be in the kernel, that would mean that they have to fix phi of G. So fix that fix. Okay, so let's say that then. So it's automorphisms of L that fix phi of G. That's equal to gamma phi of G, which is equal to G, right? So the kernel of this homomorphism is G. So remember, what we're supposed to be showing is that the quotient gamma L over K mod G is isomorphic to this right here. So we've identified the kernel, and so we know that this group mod G is isomorphic to the image, so the last thing we need to do is show that this is onto. Okay, so we just have to show that this restriction mapping is onto. So we show that the restriction is onto. Okay, so we're going to pick somebody in there, and so pick somebody in the codomain. So let's pick, say, rho in gamma phi of G over phi gamma. Okay. Now, since rho fixes phi gamma of K, and we know that K is a subset, so K is contained in phi gamma of K. This was a theorem, which theorem was this? 5.1. We know that rho has to fix K. Right? If you fix the whole thing, then you fix the stuff that's inside there also. Okay, now So I like to view rho, right? We know that rho, rho is a mapping of phi of g to phi of g, and since phi of g sits inside L, we can view rho, so let's say viewing rho as a monomorphism. So that would be rho from phi of g to L. Oh. That fixes K. And using the fact that L over phi of g is, well, it's actually Galois, so it's normal. Oh, actually, no, I don't care about normal. I care about separable, don't I? Yeah, sorry. I don't care about normal. I care about separable. So this is let's say like this Galois, hence separable. Separable. What does that tell us then? We can extend rho to some mapping of L. So there exists. Oh, you know what? Let me remind you, or let me just keep all the pieces. So how do I know this one? This is by theorem 5.4c. We can apply. So now this will be theorem 4.3. So we can extend rho to an automorphism. So there exists an extension sigma from L to L of rho that fixes, let's see now, who does rho fix? Rho fixes K, so that fixes K. In fact, how many of these such extensions are there? There are exactly this many, or the degree of this, right? So now, what does that mean? So now we have sigma that lives in gamma L over K, and sigma restricted to, oh, I need to restrict to 5G, don't I? Oh yeah, so sigma of phi of g equals rho. And now I feel like, did I say something weird here? Oh, yeah, sorry. I got a phi of g right there. That means that I can say right here, this fixes, okay. Wait, what do I want to fix? I know it fixes K. Fixes, I want, oh, sorry, I'm a little confused right here. The last two sentences. Okay, let me see. Fixes K. I can extend it. Extends to, Okay, so now sigma is in here, and when I restrict, I'm supposed to be rho. Why do I know? Okay, I know that rho fixes k over here. Rho is a mapping that fixes that, which means it fixes k. Oh, it's an extension. Sorry. I don't know. Why do I care about it? Who it fixes? It fixes k. So what? Okay. So then, sorry, I was confusing things. Sorry. So now, when I restrict sigma to phi of g, we get rho, right? Because sigma is an extension of rho. Sorry. I got held up on the fixing part when I should have been focusing on the restriction part. Okay. And so what that tells us is, so therefore, the restriction is onto. Okay, so now applying the first isomorphism theorem, so conclusion is that gamma of LK mod G is isomorphic to the image, and the image is exactly gamma of phi of G over gamma, I keep saying gamma, sorry, gamma of phi of G over phi gamma, no, that doesn't make any sense, 5k, there we go, 5k, phi gamma of k. All right, that's a long theorem, it's fairly tough. But it really amounts to just putting a bunch of pieces in the right spots. And you notice I got to keep looking at my notes to make sure that I don't screw up one step here. Anyways, okay, so now we got the theorem. And over the next few days, we're going to see how to make use of this theorem and what it tells us and what it does for us. But that's a good place to stop for now. So we'll see you next time.